So this is the second lecture out of chapter 3. So this material we're going to talk about right now is certainly one of the more difficult aspects for students in this chapter. Actually, this lecture and the next 2 lectures are pretty difficult material for most students. So basically, we're just going to do a lot of conversions in this chapter. So in this lecture, we're going to convert between moles and grams and numbers of molecules and numbers of individual atoms. So basically, using the content covered in this chapter, you should be able to answer questions like the 4 that we're gonna cover here. So if you have 11.3 grams of C3H6O2, then for example, I could ask you how many moles are present, or I could ask you how many molecules are present, or how many atoms of carbon, hydrogen, and oxygen are present. And then we'll work these other problems B, C, and D as well. Okay, so if we take this first problem, so if you have 11.3 grams of C3H6O2, whatever the molecule is, doesn't matter, you shouldn't get hung up on that. So how many moles of C3H6O2 are present? Okay, so if you're going to do that, so for these type of calculations, you will need the molar mass of the compound. So if it's not given to you, then you'll have to go ahead and calculate that first. So in the last lecture, we looked at how to calculate molar masses. So we're going to take our periodic table, right, and look up hydrogen, carbon, and oxygen and get the molar mass of 1 hydrogen, 1 carbon, of 1 mole of hydrogen, 1 mole of carbon, 1 mole of oxygen. So, but then you have to keep in mind these numbers. So this molecule has 3 moles of carbon, 6 moles of hydrogen, and 2 moles of oxygen. So we're going to take hydrogen 1.00794 from the periodic table, and we're going to multiply that by 6. Carbon from the periodic table 12.011, and we're going to multiply that by 3 because of the subscript. And oxygen, we're going to multiply that by 2. So if we multiply that out and add them up, we should get 74.08. Let me just make sure. Okay, so 74.08 if we round it to 2 decimal places. And now you want to know what is the unit associated with that number. So the unit is grams. Grams of what? Grams of C3H6O2 and 1 mole. So that's that many grams in 1 mole of the molecule. So again, you want to keep track of units in this chapter. It's going to help you get to the answer. Okay, so now we can convert grams to moles using the molar mass. So what we just calculated is the molar mass. So now we can use that to convert between grams and moles. So you can think of molar mass as a conversion factor. Just like 12 inches is 1 foot, that's a conversion factor to allow you to convert between inches and feet. Molar mass is a conversion factor that allows you to convert between grams and moles, right? So for example, you can use in this conversion factor, you can convert inches to feet by dividing by 12, or you can convert feet to inches by multiplying by 12. So for example, if you had 3 inches and you wanted to convert that to feet, you could set up a dimensional analysis. So since inches are on the top, then they need to be on the bottom here. So that number needs to go on the bottom, and then the 1 foot needs to go on the top, and then inches cancel, and 3 divided by 12 gives you 0.25 feet, right? Or if you had the opposite, if you had feet and you wanted to convert to inches, so if you had 0.25 feet and you want to convert to inches, again, you use the same conversion factor, but now since feet are on top here, then you need feet on top here. So that 1 foot goes on the bottom, 12 inches go on the top, 0.25 times 12 is 3 inches, right? So if you can do conversions like that, then you should be able to do conversions in this chapter 3 using molar mass. It's same math, right? It's just a different conversion factor. Okay, so we have 11.3 grams of C3H6O2. Let's convert that to moles. So since grams is on top, then we need grams on bottom, and so that 74.08 always has to stay with the grams, so that has to go on bottom. So 74.08 grams of C3H6O2, and then on top is the 1 mole. So basically 11.3 divided by 74.08. All right, so if you're converting from grams to moles, you're basically going to divide by whatever the molar mass amount of grams was. So if you do that, then you should get 0.153 moles of C3H6O2. Okay, so if you were going the opposite way, if I gave you moles and you wanted to convert to grams, then if you're going from moles to grams, then you divide by the number that's in front of the grams. So divide by 74.08, right? So if you had the 0.1525 or 0.153 moles of C3H6O2, then you would come back to the same conversion factor. But now since moles is on top, then you need to put moles, the 1 mole of C3H6O2 on the bottom, and you need to put the 74.08 grams on the top. So now you're just multiplying by the molar mass, and so you would get back to 11.3 grams, right? So anytime you're converting between grams and moles, it is always molar mass. If you're going from grams to moles, then you're going to multiply by the inverse of the molar mass, just like we did there. We multiplied by the inverse. If you're going the opposite way from moles to grams, then you're going to multiply straight across by the molar mass, right? Just like we did here. Okay, so now that we have the moles of C3H6O2, now we can answer the next question. We can convert to numbers of molecules of C3H6O2. So to do this, then you have to remember that 1 mole of anything is equal to how much? 1 mole of anything is equal to Avogadros number, to 6.02 times 10 to the 23rd. So if we're converting from moles to numbers of things, then we need Avogadros number. Okay, and the things in this case that we're converting to is molecules of C3H6O2. So we take the moles that we just calculated, 0.153, or it's best to not round into the end. So if you just kept all of the numbers in your calculator, and you can round at the very end. So we're going to take the 0.153 moles of C3H6O2, and so then we're going to multiply by Avogadros number. So there's that many molecules in 1 mole, right? So moles are going to cancel out, and now we're going to be left with molecules. So if you did that, you should get 9.18 times 10 to the 22nd molecules of C3H6O2. Okay, so whatever this molecule is doesn't matter, but so you just have to keep in mind now, if you're converting from moles to molecules, then you use Avogadros number. So if you're going from moles to molecules, you just multiply straight across by Avogadros number. If you're going the opposite direction, if you had molecules and you wanted to know how many moles that would be, then you would divide by Avogadros number, right? Just like the next one shows. So if we took that many molecules, so if we had that many molecules of C3H6O2, how many moles is that? Well, since molecules is on top, then we need Avogadros number on bottom. 6.02 times 10 to the 23rd molecules, and that is the same thing as 1 mole, so the mole on top, and then molecules would cancel out, and you would be left with moles, so 0.15 moles. Okay, so now that we know how many molecules of this that we have, 9.18 times 10 to the minus 22, now we can answer the question, how many carbons, how many hydrogens, and how many oxygens are there? And to do that, now we want to take the molecule and start breaking it apart into pieces. How many carbons are there? How many hydrogens are there? How many oxygens are there? To do that, you use the molar ratio in the chemical formula, right? So that's where you use these numbers at, if we want to talk how many carbons, hydrogens, and oxygens there are. So we just calculated that there's 9.182 times 10 to the 22 molecules of C3H6O2. And if we wanted to figure out how many atoms of carbon there are, well, in 1 molecule of C3H6O2, there are 3 atoms of carbon. So we just take that number, multiply it by 3. So if we did that, then we would get 2.75 times 10 to the 23rd atoms of carbon. And if you wanted to calculate how many hydrogens instead, well, there's twice as many hydrogens as carbon, so you could just take that number that's in your calculator right now and multiply it by 2, right? Because there's twice as many hydrogens as carbon. Or if we go back to the start, you could take the number of molecules, and now there are 6 hydrogens in every one molecule, so you just take that number times 6, and you should get 5.05 times 10 to the 23rd atoms of hydrogen. So this all started with what, the 11.3 grams, right? So in 11.3 grams of this molecule, there are 5.05 times 10 to the 23rd atoms of hydrogen. And now if we wanted to do this for oxygen, so if you just look at the ratio, hydrogen to oxygen is a 1 to 3 to 1 ratio. So there's a third as few oxygens as there are hydrogens. So if you have that number in your calculator, you could just divide it by 3, and that would be how many oxygens there are, right? Or you could go back to the beginning, that many molecules, and now there's 3 atoms. Is that right? 2 atoms. 2 atoms of oxygen in every 1 molecule of C3H6O2. So molecules of C3H6O2 cancel. You multiply 9.18 times 10 to the 22nd times 2, and that's how many oxygen atoms there are, which is 1.83 or 84 for rounding, times 10 to the 23 atoms of oxygen. And that's a lot of work, right? So we just answered that first question, but that was a lot of work. So you can see that this is not trivial stuff. The math is easy. All that we're doing is multiplying and dividing. You just have to know how to set the problem up. So this kind of summarizes what we just did. So we started with grams, and if you start to grams, you have to go to moles first. And you do that by using the molar mass, right? So you're either multiplying or dividing by the molar mass, depending on which way you're going. And if you have moles, then you can convert to molecules. And to do that, moles to molecules is always Avogadros number. And then once you have molecules, then if you want to convert to individual atoms, so A, B, C, D, whatever this chemical compound was, that would be where you use the subscripts and use the molar ratios, right? For every W of A, there's X's of B's and Y's of C's and Z's of D's. So you would multiply whatever the subscript is. If you wanted to figure out how many hydrogen or A's there were, you would multiply whatever number you get here by W. If you wanted to figure out how many B's there are, you would multiply whatever number you get here by X, and so forth, right? Okay, second problem. So a reaction calls for 2.5 moles of AlCl3, aluminum trichloride. So how many grams of AlCl3 should be weighed out? So you go to the balance, you weigh it out. How many grams should you weigh out if you need to put 2.5 moles into your reaction? Well, we have moles and we want to go to grams. So all we're doing is this right here, right? We're doing moles to grams. So we're going this way. If we're going that way, then we just need to multiply by the molar mass. So you need to, if you want to convert between moles and grams, you need molar mass. So if it's not given, then you calculate it yourself. So you need your periodic table. If you look up aluminum, it's 26.9815 grams per mole. Chlorine's 35.4527, but there's 3 chlorines in the molecule. So now multiply that out, add it up, and you should get 133.34 grams of AlCl3 in every 1 mole of AlCl3. Okay, so now we can do the dimensional analysis. So we have 2.5 moles of AlCl3. Since moles is on the top here, then moles have to be on the bottom here so that they can cancel each other out, which means this needs to go on the bottom. So 1 mole of AlCl3 goes on the bottom, and then on the top goes this number, the 133.34 grams of AlCl3. So now your moles are going to cancel, and the only unit left is grams, which is what you want. So again, if you end up on the right unit, you probably did the math right. So you would get, as an answer, 333.35 grams. So you need to go to the balance, weigh out 333.35 grams and put that into your reaction. And if you did that, then you just put 2.5 moles into the reaction of AlCl3. Okay, next problem. So a sample contains 7.21 times 10 to the 24 molecules of NH3. How many grams is that? So how many grams are in that sample? So if we go back here, so we are starting right here, and we want to go to here, to grams. So if you want to do that, you have to go through moles first. So you have to convert molecules to moles. Once you have moles, then you can convert that to grams. So if we want to convert molecules to moles, how do you do that? You use Avogadros number, right? And you just have to know, are you multiplying by Avogadros number or are you dividing by it? Well, there's 6.022 times 10 to the 23rd molecules of NH3 and 1 mole of NH3, right? So molecules to moles, you need Avogadros number. And then once you have moles to grams, then you need molar mass. So since molar mass is not given, you got to calculate it yourself. So get your periodic table. Hydrogen's 1.00794. There's 3 hydrogens in this molecule. Nitrogen's 14.0067. There's 1 nitrogen. So you add those up and you get 17.03 grams per mole. So we could do this one conversion at a time, or we could set up multiple conversions at a time. It doesn't matter, however you want to do it. So I'll show you how that we could just do the multiple conversions to get all the way from the start to the end through a sequence of calculations. So we start with that's how many was given, 7.21 times 10 to the 24 molecules of ammonia. We want to convert that to moles. We want to use this conversion factor. Since molecules are on top here, we need molecules on bottom here. So 6.022 times 10 to the 23rd molecules of NH3 is 1 mole. So then your molecules are going to cancel, right? Molecules cancel out. Now we have moles, and we want to go to moles to grams, so then we can use this conversion factor. So since moles are on the top here, then we need moles on the bottom here, so that's 1 mole. So 1 mole of NH3 is 17.03 grams of NH3. So now moles are going to cancel out. And the only thing left is grams, which is what you want. That's the unit you want to end up in. So we're going to multiply the tops, and we're going to multiply the bottoms, and then we're going to divide those 2 numbers, and that's your answer. So if you do this, you should get 203.9 grams of ammonia. And if you notice here, I'm not really paying attention to significant figures. I get a little sloppy like that sometimes. I don't necessarily expect you to keep track of significant figures in a calculation unless I explicitly ask you to, right? So if the question is me trying to test your knowledge, if you know how to keep track of significant figures, then I'm going to tell you, report this answer to the right number of significant figures so that I can test you to see if you know how to do that. But if I don't explicitly state that, then I'm not that picky, you know, how many significant figures are in your answer, but hopefully you recognize how to do that if you needed to. Okay, so last question. So what is the mass in grams of 1 atom of sodium, Na? So what is the mass in grams of 1 atom of sodium? So to answer this question, you have to know how to understand that number. So again, there's units associated with that number, right? What is the units associated with that number? It's 22.9898, either AMU, atomic mass units per 1 atom, or 22.9898 grams of sodium per 1 mole of sodium, right? Okay, so this is the one that we're going to use for this calculation. So there's that many, 22.9898 grams of sodium and 1 mole of sodium, and we need to get to grams per atom. So since we have grams on top here, we need grams on bottom here. So wait a minute, let me think. We want grams per atom. Yes. No, we don't want to cancel out grams. We want to get rid of moles, right? We want to end up in units of grams of sodium per atom of sodium. That's what the question asks us. So we don't want to get rid of grams. So we don't need the bottom to be grams. We need the bottom to be atoms, because we need to have atoms on the bottom. So this is where you have to recognize, okay, if we want to convert moles to atoms, what do you need to convert moles to atoms is Avogadros number. So this is a number of things. So Avogadros number is going to convert moles to a number of things. Well, there's 6.022 times 10 to the 23rd atoms of ammonia in 1 mole. Not ammonia, sorry. Sodium. Na is sodium. Stuck on this problem number 3. So 1 mole of sodium is 6.022 times 10 to the 23rd atoms of sodium. So now moles of sodium cancel, and now we have grams per atom, which is what we wanted. So you take 22.9898 and divide it by 6.022 times 10 to the 23rd, and you should get 3.818 times 10 to the minus 23 grams of sodium per every 1 atom of sodium. Okay, so those are some difficult calculations until you wrap your mind around how to do them, and basically you recognize how to do these conversions. When do you use molar mass? When do you use Avogadros number? When do you use the molar ratio, the subscripts in the formula, right? But again, if you learn to think in terms of units and keeping track of units in your calculations, then chemistry, math, physics, engineering, everything that requires you to calculate something becomes much, much easier. And if you work with units, and if your units work out at the end, you end up with the right unit, your answer is probably correct. So it's a great way to check your work. Okay, we'll stop there.